Okay, folks, let's get started. So, are everybody's Boids behaving? Sort of. Are most people in the phase, the optimization phase, trying to get the most Boids as they possibly can? Okay. If you want to talk about any of that stuff, I'm very happy to. Otherwise, I had sort of this realization a couple days ago that I'm going to be asking for your final project proposals in 2 weeks. I'm going to ask for you to turn those in when you do your week 2 checkout for Lab 3. And that's so that we have time to look at it and provide feedback so that by the time we finish Lab 3, you can start right up on your proposed project idea. But given that I'm going to ask for you to propose these projects in about 2 weeks, I thought it might be productive to spend a lecture just sort of shotgunning ideas and trying to get folks' wheels turning about various things that they might consider working on. So I have a big list here of a bunch of sort of hallucinations that I'm just going to go through in no particular order. And if you want to talk through any of these in more detail, I'm very happy to. But otherwise, I'm just going to sort of start at the top of this list and go through a bunch of project ideas that you might consider. Some of these are based on things that folks have done in the past. Others are things that I haven't seen anyone do, but depending on your inclination, you might be interested in. And I had started sort of vaguely dividing these notions into graphics projects, robotics projects, that kind of thing, and then it got all messy. So this is going to be in no particular order at all. So I'm going to start with the first set of notions I have here are those vaguely related to pretty mathematics. So folks that are interested in things like fractals might be interested in these kinds of projects. The first one on my list here is, have people heard of diffusion limited aggregation? Ever heard of this concept? So if you have gotten into your car on a frosty morning and you look at the windshield and it's got this sort of intricate crystallization pattern of ice crystals on the window, the diffusion limited aggregation is an algorithm that generates patterns like that. So let me just pull up a picture. And you can read about the details of this, but I'll just sort of summarize that approximately what's going on here is, let's see, let's make that bigger. So approximately what's going on here is you have a bunch of particles sort of randomly bouncing around. And if they happen to bump into a particle that is a part of a structure that is fixed and growing, then it sticks. And so you allow for this algorithm to run, and depending how you initialize it, you can end up with these really pretty sort of crystal structures growing out from a central origin. Or you can do other fun things like have the crystal structures grow off of a drawing or text or something. So you could have your name on the screen and then have crystals grow off your name. These kinds of projects are really fun. They generate really, really pretty pictures. And one of the interesting things that you could try to optimize here is how many particles compose your diffusion limited aggregation system. You could get a lot because unlike Boids, in this system, no particle has to know about the other particles. It has to know when it should stop moving, but all the particles are largely completely independent, which means that you could generate a ton of these things. So you all are generating on the order of maybe 400 to 700-ish Boids. You could get, I would think, thousands or tens of thousands of particles. And you might consider other what's called particle systems. These are systems kind of like Boids in that you are animating a whole bunch of individual particles, but unlike Boids, those particles don't know anything about each other. They're completely independent. And you can do things like have their velocity changes not be a function of the states of nearby particles as they are in Boids, but instead a function of where they are on the screen. So you could sort of imagine superimposing a vector field onto the screen that describes how a particle at this position should move if it finds itself at this position. And depending how you construct that vector field, you can generate beautiful simulations of things like smoke or water or explosions. In fact, if you watch the old Star Wars movies, those in-space explosions, I believe, are all particle system simulations. And then the other thing that you can play with is have the color of the particle also be a function of its position on the VGA screen. So you can imagine, for instance, spawning tens of thousands of particles down at the bottom of the VGA screen and generate some vector field that sort of approximately goes like this, and then change the colorization so that they go from maybe white or blue up to orangey up to yellow, and you could generate a beautiful candle flame. And then maybe make a breeze go across the screen so that the candle flame goes like this. I think on this system with 2 cores running at, overclock it to 250 megahertz, you could get a ton of particles to make really, really compelling particle simulations. So that's something you might consider. You could do fireworks and stuff like this as well. You might alternatively consider, have people heard of, this is another sort of mathy project, but diffusion reaction equations? I love these. So let's see if there's a pretty picture here. Kind of. Here's one. So a diffusion reaction equation, it's a system of coupled differential equations. And what that set of coupled differential equations is supposed to model is the evolution of some system from disequilibrium towards equilibrium. So we imagine some system where we have 2 chemicals, sort of a substrate chemical and then another chemical that we splotch onto the substrate chemical. And the set of coupled differential equations models the diffusion of those splotches of chemicals out across the other chemical and the reaction of the 2 chemicals into an inert chemical that doesn't react. And depending on the initial conditions that you set up and depending on the knobs that you turn in these differential equations, you can generate really interesting patterns. And they look interesting in their own right, and then you turn the lobes a little bit and suddenly you go, oh my God, those are leopard spots. You turn the lobes a little bit more and you go, those are giraffe markings. So one of the first papers about these systems was written by Alan Turing, of all people, one of his many contributions to many fields. It has some cheeky title that I can't remember, but it's something like How the Tiger Got His Stripes or something like that. But in any case, the system under consideration was animal coats. So you can generate these systems to develop, you could, as a final project, try to develop a system that builds giraffe patterns, and then you could also build just totally imaginary animal patterns, which might be kind of interesting. Did you have a question?
Oh, I was just asking you if that's the one that you used to simulate zebra patterns before you.
Yes, it is, yeah. You might also consider other sorts of algorithmic generation of natural things. There are algorithms you can look up that will generate snowflakes, fractal snowflake generation. Those are kind of interesting. You're all, I think, at this point familiar with the Mandelbrot set. There's an example in the course demo code that generates the Mandelbrot set. And maybe we've talked about it a little bit, but the Mandelbrot set has been called the most beautiful structure in mathematics. I think a title that it earns. It's really pretty. It has this interesting feature that the edge of this structure is infinitely rough. That is to say, you could zoom in on a boundary here, and you could keep zooming in forever, and you would keep finding new structure there. What many folks have discovered if they've run this example on the RP2040 is generating this whole set on the RP2040 takes a considerable amount of time. Reason for that is in order to figure out which points are in the set and which points are outside of the set, we have to run an iteration, which takes some time. So there are a few flavors of final projects based on the Mandelbrot set that I might imagine. One is if folks are really into optimization, if you really like the optimization part of the Boyd's lab, for instance, you could try to accelerate the computation of the Mandelbrot set to the greatest extent that you possibly could. Looking into the deepest, darkest corners of the data sheet to try to figure out ways to make this happen as quickly as you can possibly manage. The other interesting thing that you might do is you say, okay, I'm not going to make a picture of the whole Mandelbrot set. I'm going to zoom in on a little square here that I find interesting and that doesn't require quite as much time to compute. And I will calculate and render that square. And then I'm going to build a user interface that allows for the person playing with my project to pan and zoom around in that smaller square. That could be kind of interesting. You might incidentally build essentially the same project with Julia sets. This is another set of fractals, closely related to Mandelbrot sets, that generate a whole family of different but equally gorgeous patterns. So you can imagine building a Julia set generator. We had a group do this using the PIC32 in a past year, and it ended up beautiful. They got very obsessed with trying to find really, really pretty Julia sets. You might be interested in doing something like that. You might be interested in, folks know what cellular automata are? Okay, so a cellular automata, the most famous cellular automaton, I believe, is probably the Game of Life, developed by the mathematician Conway. This too, there's an example of this in the VGA demos. A cellular automaton, I'll just summarize, is a system where we take the 2D plane and we grid it up into cells, and then we come up with a set of rules that describes when certain cells turn on or off, or from black to white, or dead or alive, whatever sort of binary vocabulary you want to use to describe the state of a cell. And depending on that set of rules, you can generate really, really complicated behavior out of the system. So in Conway's Game of Life, the rules are summarized here. A particular cell can observe its neighbors. That is to say, a cell can see the neighbors to the left and right, up and down, and on the diagonals. So it looks at the state of those neighbors. If the cell is alive and 2 or 3 of its neighbors are also alive, then it survives the next generation. It stays alive. Alternatively, if a cell is dead and it has exactly 3 neighbors that are alive, in the next generation, it transitions from dead to alive, black to white, whatever, it changes state. And all other live cells die in the next generation, and all other dead cells stay dead. So it's a really, really simple set of rules. So you have some initial, perhaps random configuration of cell states. Each cell looks at its neighbors and decides, am I going to stay dead? And am I going to transition from dead to alive or from alive to dead? We update the whole grid, and that's the next generation. And then we do it again and again and again. And this particular set of rules generates really interesting stuff. For instance, some of these patterns that it generates have names. So if you start with this initial configuration, you can generate what's called a Gosper's gliding gun. This creates structures that propagate across the 2D plane. There's a whole family of these structures that you can generate to demonstrate interesting behaviors. There are certain initial conditions that have the property that they grow infinitely. And in fact, the VGA demo included in the demo code for this course is one of those initial conditions where you click go and it just propagates, it continues to grow forever. Conway's Game of Life is Turing complete. You can build CPUs in Conway's Game of Life, and people have done so. If you Google computer implemented in Game of Life, you will find a website by a person whose name I really wish I could remember, because I'd love to point you to his webpage. But in any case, this person figured out how to implement logic gates in Game of Life, and then use those logic gates to build simple CPUs entirely in Game of Life. You can build Game of Life in Game of Life. I've seen this on YouTube. God bless these folks. So in any case, this is a very, very famous example of a cellular automaton, but there are other examples of cellular automata that you might also be interested in implementing. If you're interested in such things, there's the mathematician Stephen Wolfram spent a lot of time studying these systems, and he has a whole bunch of publicized cellular automata, sort of rules by which you evolve these systems, and they generate varying interesting patterns. So this might be kind of cool. For this one too, because you have some demo code from which to start, a reasonable final project would be to do something interesting with Game of Life. Right? Exactly what that is, I'm not really sure, but we could talk about it if you're interested in these sorts of things. Yeah. More fractals. I love fractals. How about the diamond square algorithm? So the diamond square algorithm It's an algorithm for fractal landscape generation. So if any of you are into video games, maybe you play Skyrim, something like that, any of these games that involve, interesting mountainscapes and landscapes, it's often those case in video games like that those landscapes are generated algorithmically. There are a few algorithms that allow for you to do this. One's based on FFTs. Another one is this diamond square algorithm. And essentially the way that this works is you start with a flat plane, and then with increasing resolution, you change the elevation of, starting with just 4 points in that plane, you randomly change their orientation. Then you step in, and to a greater resolution, you change the elevations within that plane, and so on and so on and so on. So to finer and finer resolution, you are adjusting elevations from this initially flat 2D plane. And you allow for this to run, and at the end of running this, what you end up with is some randomly generated mountainscape. And then the interesting thing that you can do is you could say, okay, I am going to color, any elevation in this landscape that is below a certain threshold, I'm going to make blue, which is sort of like filling the valleys with water, right? You're sort of putting lakes down there. And then maybe as the elevations go up, you transition from green to white, and you would generate a simulated mountainscape that includes water and, a tree line that goes up to a rocky or snowy peak. In order to make this really interesting, probably the other thing that you'd like to do for a final project based on this is add that extra green bit to the VGA. It might be nice to have a little bit of extra color resolution here in order to make your landscapes interesting looking. That's not so bad. We can help you do that, but I think you'd benefit in this case from having a little bit of a richer color palette. Yeah. A couple more fractals. How about L systems? People heard of L systems? So an L system, there's a whole bunch of different L systems. It's essentially it's a similar sort of rule-based algorithm where you start with some base sequence of characters and you map a behavior to each of those characters. So maybe one of the characters means go forward this far, another one means turn right by this much, another one means turn left by this much. And then over a series of generations, there are rules by which you start with this initial string of characters, and then there's rules by which to go to the next generation, you replace a specific character with a new set of characters. And then you do it again, you replace each of, so it's growing, right? You're getting a longer and longer string of characters, each of which maps to an action that you end up rendering on the VGA screen. And these are most frequently used to generate really gorgeous plant structures. And you can play with these rules, and depending on the knobs that you turn, you can generate things that look like, I don't know, elms, and then you can change it a little bit and you end up with what looks like wheatgrass. So you end up generating a whole family of different plants using this algorithmic algebra. I love these, and these too, it's interesting to then differentially color because you could put little leaves at the end and stuff like that. It looks really real. The other example of an algorithmically generated plant, one that many of you have seen already because this one too is included in the demo code, is the Barnsley Fern. This one is generated using a quite different algorithm. Rather than being sort of an algebra of symbol replacements, this instead, there's a series of functions that describe where you, so the way that this starts is you draw a point, and then you apply a function that moves you to a different place in the 2D plane. You draw another point, move to a different place. So you're drawing dot, 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 dot. And those dots end up building up this fern shape. And this too, you turn the knobs a little bit and you get a different shaped fern. And then you turn them too far and it doesn't look organic anymore. You sort of lose the illusion. I love these kinds of things, these sort of vaguely aesthetic mathematic projects I find really interesting. One more in this direction. Have people heard of the dragon curve? Has anybody here read Jurassic Park, the book? Original book. Okay, if you read Jurassic Park, each chapter of that book starts with a picture of the dragon curve. So chapter 1 starts, I think, with this picture. Chapter 2 starts with this picture. Chapter 3 starts with this picture. And it builds up more and more complicated structures. This, too, it's a self-similar fractal curve. So you start with some base shape, and then you make self-similar copies of that shape, and it ends up building up a complicated structure. It's called the dragon curve because if you kind of squint at it, it vaguely looks like maybe the shape of a dragon. These are interesting too, I think. So challenges here would be, how fast can you render this, that kind of thing, and how much depth, how many fractal layers deep can you render? So when do you bump up against, for instance, a memory constraint where you can no longer hold any more information about the dragon curve? It'd be an interesting thing to learn for the RP2040. Okay, I said last one. I wanted to show you one more, the Hilbert curve. Have folks heard of this? This is what's called a space-filling curve. So it's a line, but this line is drawn in such a way that it's another fractal curve. If you run this over and over and over again and add fractal resolution, it ends up filling the 2D plane. So it's a line that entirely fills the 2D plane. What's interesting about this, and those of you that are fans of the YouTube channel 3 Blue 1 Brown might be aware of this. What's interesting about this is this curve lends itself really nicely to sight-to-sound projects. So for instance, you could take a picture and plop it over this Hilbert curve here, and then this curve would describe the order in which you should traverse the pixels that compose that picture to get information about them. You associate the color or the intensity of that pixel with a frequency. And then you take this Hilbert curve and you stretch it out into a line, and you use direct digital synthesis synthesizers to generate the frequencies associated with each of the pixels that you saw so that you get a unique sound associated with a picture. We had a group that did this 2 years ago, sort of a proof of concept thing, where the pictures that they generated were very simple ones. It was just 8 pixels by 8 pixels, and each pixel was either black or white. Right? So it's still, that's 8 by 8, that's still 64 pixels, which means they generated 64 direct digital synthesis synthesizers, each of which would synthesize a different frequency. And then they would traverse those 64 pixels by following the Hilbert curve. If a particular pixel was on, then that synthesizer would turn on, and they would synthesize the frequency associated with that pixel. If it was off, then they wouldn't. So what you ended up with was a particular composition of sine waves, a composition of frequencies that was unique to that particular picture. And the folks that built this played with it long enough that you could draw a smiley face on the screen, and they could close their eyes and you'd play it and they'd go, I think that's a smiley face. And then you could make it a frowny face, and they could go, it's transitioned to a frowny face. And then, they couldn't, it would take obviously a long time to really train your brain to be good at this, but they could tell you, if you went in and turned on 3 pixels and you put them all sort of up here, they could say, I think this is a picture with white pixels in the upper right corner or the lower right corner or wherever it may be. They could tell you some basic information about the visual content of the photo just by listening to its associated sound. It was really interesting. Really interesting project. You might consider doing something similar. Okay. Other kind of algorithmic projects that might be fun. People heard of ant colony optimization? Ant colony optimization algorithms. I feel like there could be an interesting project with a really interesting visual component to these algorithms. Where so let me describe the algorithm first. Suppose you have an ant colony, it's sitting here, and there's a food source over there. How is it that the ants find that food source? Well, the way that they do it is the ants, if you stare at ants for a long time, which is actually weirdly fascinating to do. If you find a bunch of these on the sidewalk, just stare at them for like 10 minutes and watch what they do. What you'll discover is many of them are kind of just random walking. And then suppose one of those random walking ants encounters a food source. It makes its way back to the colony and it deploys a pheromone trail as it goes. That pheromone trail has a decay time, so it starts to evaporate away. It gets back, another ant encounters the pheromone trail that that ant left and goes to the food source and reinforces the pheromone trail on its path back to the colony. So there's a positive feedback loop here where that pheromone trail is getting reinforced and reinforced and reinforced. And ultimately, what you end up with is a trail of ants from the colony out to the food source that is close to optimal. The path that they end up taking is a close to optimal one. So wouldn't it be interesting to treat this kind of like a particle system, generate as many ants as you can, build a user interface that allows you to plop a food source over here, and then let the algorithm go. Have ants wander around the screen, have one encounter the food source and make its way back, have some visual representation for the pheromone trail and show it dissipating, and then show other ants encountering it and reinforcing that pheromone trail so that you can observe how this path that they take to the food source evolves over time. I think this would be so cool to visualize. Entirely incidentally, in real ant colonies, there can sometimes be there's a bug in this system. Suppose that pheromone trail accidentally ends up in a circle. You end up with what's called a ring of death, where, let me see if there's pictures of this, ant ring of death, where, like I said, there's a positive reinforcement loop here. So if that pheromone trail ends up in a circle and other ants aren't that smart, right? They're just following the pheromone trail. They end up reinforcing that circle. The whole colony will march in a circle until it's dead. Pretty dark, right? Pretty dark. But it would be kind of interesting to see if your RP2040 based simulation of this system, could you cause for this to occur? Could you generate an artificial ring of death on the VGA screen? Okay, I talked about particle systems. Another one that might be fun is in like your intro programming class. Did people play with turtle graphics? Yeah, so turtle graphics being essentially, it's a simple program where basically there's a little turtle on the screen. The turtle's either leaving a trail behind it or it's not. Well, in some systems, it's always leaving a trail behind it. But in any case, you write programs for it that describe behaviors like move forward this far, turn right by this much, turn left by this much, and so on. You can do really interesting things with turtle graphics. You can make really compelling pictures. Yeah.
In fact, that's equivalent to an L system.
Yeah. L systems, you'll remember, I described them as this string of characters that describes behaviors like move forward, turn left, so on and so forth. It's what turtle graphics is doing, is what Bruce is suggesting. I saw an interesting examples of a turtle graphics project from the YouTube channel Numberphile, which I'm a big fan of. In any case, this guy had implemented a turtle graphics program where the turtle always moved forward the same amount, 1 unit, however far you want for that to be. But then the amount by which it would turn each frame was somehow computed using pi in such a way that it was an irrational number. And what it ends up generating are these really interesting spiral patterns that are unpredictable, right? Because it's being generated from a completely irrational number. So you get these really pretty spirally patterns, and it's an example of this system that you don't know what it's going to look like until you make the thing do it, right? That'd be kind of cool to try. You could make an artistic project. These are rare, and I think they're rare because they're hard. So suppose, I've been pondering this question, okay? Suppose someone comes to you and they say, okay, electrical engineer, I would like for you to build something for the Louvre. And it's not, I'm not asking you to build a lighting system to illuminate artworks. I want you to build something that feels appropriate in an artistic space, but that is engineered by an electrical engineer. What do you build? What does an electrical engineer build that makes sense in a space like that? And I have some speculations about the properties that such a project would have. But I think actually that's a personal thing. I think my answer to that question would be a personal one, and your answer would be a personal one. It'd be pretty fascinating to ponder this for yourself. Try to think about what are the properties of the thing that I would build that would make sense in a space like that, where the notion is that people would come up and interact with it in some way. Maybe they look at it, maybe they listen to it, maybe they touch it or feel it in some way. Build a project that is compelling, that holds people's attention in the way that art does. That's a hard problem. But if anybody wants to try to undertake that, it could be really interesting. I have no idea what that looks like. Okay. If folks are interested in history, let me take a step back for the moment and say, I'm sort of shotgunning all these ideas at you, with the hope being that maybe this just sort of gets your wheels turning. When you're trying to come up with a project to do, the exercise that I recommend that you go through is start by making a list of all the stuff you're curious about. You don't have to know a thing about the thing. Just what are you curious about? I'm really interested in blue whales. I don't know. I'm really interested in how whales communicate, or I'm really interested in Russian literature. Whatever it is, it could be anything. Make a long list of the stuff that you're curious about, and then once you have that list on your own, or with the help of me and Bruce and your TAs, we can figure out something that you can build that allows for you to explore that interest. So the project becomes the mechanism by which you learn about this other thing that you're curious about that may have absolutely zero to do with engineering. And you might also make a similar list that includes all the stuff, all of your hobbies outside of engineering. Do you like playing video games? Do you like playing music? There's a whole bunch of interesting final projects that you could do in the sort of video game direction. We've had students hack video game controllers so that they could cheat in fighting games. With tremendous success, they've been able to do this. We've had students build their own video games. One student built a gorgeous replica of the Google Dino game. Very, very playable with all the sound effects and the correct little icons and everything. We had one group, God bless them. They made a perfect recreation of the first level of Pac-Man. And I say that, and you think about the old arcade Pac-Man games, and you go, okay, like, it can't be that hard. Oh boy, is it. You should look up the rules that govern a Pac-Man game. They are more complicated than you realize. Every one of those ghosts, anybody know the names of the ghosts? Inky, Blinky, Pinky, and Clyde. Every one has a different set of rules that governs how it moves, and those rules can change based on the position of Pac-Man. There is a set of rules about when the little fruits appear. There's all these rules, and this group implemented all of them. They even implemented, apparently there was an end of game bug in Pac-Man where the screen would sort of split. They implemented that as well. They just did the first level, but it was a full semester project just to get that first level perfect. They were all mechanical engineers too. They figured all this out.
I heard someone ran Doom on.
That was going to be the next thing on my list. I always hesitate to recommend this because maybe every 2-3 years someone says, I'm going to go for it. I haven't seen it successfully done yet. Can you get Doom to run on the Pico? Right? This is an old trope, but if you Google Doom code GitHub, let's see, id Software, John Carmack's company, all the source code for Doom is available. It's all right here. Can you port this to the Pico and get it to play on the VGA screen? Do not undertake this lightly, right? But it could be a fun challenge for someone. And incidentally, this repository has a nice note from John Carmack himself, written in 1997, which you can read.
Actually, the guy who made it actually work.
What's that?
That guy actually made it work.
Yeah, I have seen. I think someone did get it to work on the Pico.
Yeah.
Yeah. Could be interesting to try. So if you're into video games, you know, here's a flavor of project you might be interested in. Maybe you're interested in history. Maybe you say, I'm really interested in World War II code breaking. What project could I do there? Well, do people know about the Enigma machine? This is an absolutely fascinating machine. It's an enciphering machine. So what that means is it takes a message in plain text and it turns it into cipher garbled text. So it takes a message and just makes it nonsense. This was used throughout World War II by actually a number of different nations, but most extensively and most famously by the German army, by the Nazi army. This was how they were encoding all of their transmissions. And there was a tremendous effort by Alan Turing and his colleagues at Bletchley Park and some other people to try to break the Enigma machine. And they did it. The machine that they did to break the Enigma machine is called the Bomba. And actually, if any of you take 5760 next semester, I think a fantastic final project in the FPGA's class would be to build a Bomba machine. So you could, if you're into this history, build an Enigma machine this semester, implement it on the RP2040, build a Bomba machine next semester, and crack your own Enigma machine. I've been I need to actually try to implement this myself to see how difficult it is, because I feel like it would be such a fun 5760 project to say, okay, build a Bomba machine, here's an encoded message, you're done when you tell me what it says. I just think that would be, and give everyone a different message, right? So as soon as you can tell me what the message says, you're done, and there's no arguing with that, right? The only way you can crack it is by correctly building the Bomba machine. But this is, so how does this actually work? It's composed of a bunch of different pieces. There's what's called the Stecker board, which maps a particular key to another key. So say I push an A, there's a bunch of removable plugs that allow for the user to map A to, say, F or whatever, right? So there's a tremendous number of mappings that you could do there. So there's a Stecker board. That maps a particular keystroke input to another key. That goes into a series of rotating mechanisms that then further scramble those letters. Each pass through one of these rotors maps the letter that was previously mapped by the Stecker board to another letter. Next rotor maps it to another letter, goes to a reflector board, comes back through the whole system, through the Stecker board, and back out, and a particular light bulb associated with a letter illuminates so that I push A, maybe G lights up, and I write down G, and that is my enciphering for the letter A. And by the way, every time you push a key, the rotors click. So it's changing its configuration as you write. So you can do the math on the number of possible configurations of this machine, and it is astronomical. It's so large that I think if you were able to test a particular configuration every millisecond, you wouldn't be able to get through all of them in the lifetime of the universe. I think that's the piece of trivia. In any case, it's huge. It has a weakness that those of you that are interested should Google and learn about. There is a weakness to this machine that was exploited by Alan Turing in his construction of the Bomba machine that allowed for them to crack it. An interesting piece of historical trivia is it was a big secret that it had been cracked. They did not want to reveal that they knew how to decipher these messages, and the project for cracking this machine was called Project Ultra. It's a fascinating piece of history that you can learn about. And if you're interested in this history, doing something like this is such an amazing way to learn about it, right? You can read all the books you want about Enigma machines and such, but actually building one is such a unique peek into the problem that folks like Alan Turing were pondering at this time. It's such a rare peek into the mind of this interesting historical figure. And then even more so if you go on to build a Bomba machine. It's such an interesting way to sort of get to know this person and what they were thinking about. There are at least two of these that you can go see. One is on display at the Spy Museum in Washington, D.C. 2 years ago, I drove to Washington, D.C. specifically to see this thing, and the museum was closed, so I have to go back. But I want to go see it. You can go to look at a real one in D.C. There's one on display. So that could be interesting. You could build a gravity simulation. We're changing gears here. But suppose that you could build something like a particle simulation where you try to simulate the n-body problem. Any of you that have taken like an astrophysics class know that this is sort of a canonical problem, is simulate the gravitational interactions between n different bodies, n being as many as you can get. And this too would be a fun optimization challenge because there's a lot of inverse squares associated with gravitational interactions that you are going to want to speed up in every way that you possibly can. So that could be pretty cool. How much time do we have? Oh my gosh, I'm like halfway through. Okay, so another flavor of projects you might consider. How about sensory augmentation? So we all have a certain list of senses. We can see, hear, smell, taste, touch. Could you add another one? For instance, I always want to know where north is. Can you build a device that adds magnetic field sensing to me in a way that is not annoying? There was one group in the past that did this with a belt. So they modified a belt so that it had a bunch of piezo shakers on it. And then that belt included a microcontroller that communicated to a magnetometer that could detect north. And they would vibrate in the direction of north. And you wore this belt. This was actually before my time, so I've read about this project. But you wore this belt, and an interesting thing happens where after a while, your brain stops noticing the buzzing, and you just know where north is. You get used to the buzzing. You don't really notice it anymore. It doesn't enter your consciousness, but you just know where north is. There's some evidence, by the way, that there are some animals that have this sense. Migratory birds, for instance. How the hell do they know where they're going? There's some evidence that they are sensing magnetic field and following Earth's magnetic field lines to a destination. If you're looking for other senses to augment, you might consider looking at other animals. I believe it's the case, for instance, that cuttlefish, if you look at the shape of a cuttlefish's eyes, they're sort of weird and W-shaped. I believe that their eyes are giving them polarization information about light, which if you are an undersea animal, polarization information, I believe, can give you some information about orientation. So cuttlefish have a polarization sense. We don't have that. Could we add that?
You do have that.
We do?
Yes. You look, it's not very good, but if you look up, do a Google search on Haydinger's brushes.
Haydinger's, like so?
It's spelled the way you guess, yeah. There's a fairly weak polarization sense.
Interesting. Okay.
Now, if you could make a trainer so that you got good at that, it's trainable. It's trainable.
That'd be really cool, right? I had a friend that got a little too obsessed with this sensory augmentation idea, and he got a magnet embedded underneath the skin of his fingertip so that he could put his hand near live wires and sense that they were live. He read a few too many sci-fi books. Yeah. How about voltage sensing? I believe it's the case. Bruce, you can maybe confirm this. Electric eels and such, are they able to measure ambient voltages?
They have, electric eels are covered with voltmeters.
Okay.
The term is ampules of Lorenzini. But they're little pits in the skin, and they solve Laplace's equation around their own body to find out where insulators are in the water.
It's awesome. So anyway, the whole sensory augmentation direction is an interesting place to go with final projects. A whole different flavor of project is it would be kind of interesting when we program the RP2040 right now, we do so by holding down the button and drag and dropping the program over to, it ends up going into external flash memory. Could you build a bootloader that would allow for us to program the board through light, that we could flash light at some light sensor and reprogram the device just by flashing light at it? Could you do it acoustically? This, incidentally, it's a problem that's worth solving if you're interested in swarm robotics. People may be aware of the kilobots. This was the first swarm of 1,000 robots. It's basically intractable to individually plug each of these robots in, program it, plug the next one in, program it, particularly if you're debugging, right? So I believe it's the case. I have to confirm this, but I believe that all those kilobots were programmed by light. So above the table that they were operating on would be a big light that would flash, 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 flash. That would reprogram all of them. So there was a bootloader on those that was looking at optical information and translating that into a program. It'd be pretty cool to try that on the RP2040. You could generate, oh Lord, spectrogram images. So there is a community of people that are really interested in, oh, those are all spooky. Let's see. Let's find a better one. Here, okay. So A spectrogram, as many of you are aware, it's essentially a 2D FFT. It's the time history of the frequency content of some sound, or any signal really, but we'll say sound, so that each vertical slice here represents an FFT taken at a particular time. And you, instead of representing the amplitude by sort of the height of the FFT, we instead colorize based on the intensity at that frequency, the power at that frequency. And so what you can do is, and then the spectrogram includes a whole bunch of such times so that over the course of time you can see the frequency content in a sound. This, incidentally, is how folks study bird songs. You can look up the spectrograms of bird songs and it shows you the frequency content of different bird songs. Can you generate sounds such that their spectrogram create images? That'd be kind of cool. You could modulate a direct digital synthesis synthesizer. So you can imagine a DDS synthesizer is producing one frequency, which on a spectrogram, if it never changes, looks like a line across the spectrogram. If you modulate that frequency into a wave, so it goes ew, 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 what you would get out is a sine wave on the spectrogram. Could you modulate it to write your name in cursive? Maybe. With the understanding that you can't write backwards, so it gets a little complicated. But maybe you could figure out how to write your name on a spectrogram. It'd be pretty wild. You could do those oscilloscope images that I was talking about previously. So do a Fourier decomposition of a 2D collection of points, describe a trajectory through those points, and then generate a bunch of DDS synthesizers that will approximate that trajectory in the 2D plane to generate an image on the oscilloscope and an associated sound. Or alternatively, drop the fundamental frequency of those direct digital synthesizers from something that's audible to instead something that's within the realm of possibility for, say, a stepper motor, and draw the pictures on an etch-a-sketch by driving stepper motors to turn the knobs. That'd be pretty neat. You could do sound localization projects. So compared to the speed of the RP2040, sound is pretty slow. So if you had a collection of microphones communicating to the analog to digital converter on the RP2040, you could measure the amount of delay associated with a sound hitting this microphone versus this microphone and deduce the direction from which the sound came. So wouldn't it be neat, for instance, to you could build a device that sits at the center of a table and maybe there's I don't know, some sort of directional microphone for capturing voice on it. And when someone talks, it automatically turns and points the microphone at that person. And then someone else speaks and it turns and points it at the other person. Some sort of project in that direction could be interesting. Detect the direction of a clap. You could implement head transfer functions. So you have an ability that you may not have thought much about, but you're pretty good at determining the direction from which a sound came. The reason that you're good at that is your ears are separated in distance. So there's some distance separating your two ears. And furthermore, there's stuff between your ears. There's hair and there's a head. And then within your ears themselves, there's these little folds that act like interferometers. The folds are sized just about right for sound waves. And so what happens is you hear a sound, it hits one ear, a small amount of time later, assuming that the sound is coming from some oblique angle, it hits the other ear. So there's a time delay between hitting this ear and hitting this ear. And there's also some morphing of that sound as a consequence of passing over your head and ears and so on. And you can develop a function that approximates that so that you could generate a synthesizer and then implement one of these head transfer functions so that you're sending slightly different sounds to the left and right channels of the DAC, each of which goes to a different earbud. You put it in the earbuds and make it sound like there's a fly flying around your head. If you Google head transfer function on YouTube and put headphones on and listen to some of the examples, they're really compelling. They can really trick your brain into thinking that sound is coming from one place or another place. You could do all sorts of synthesis projects. You could synthesize various animal calls. Birds are a fantastic one, particularly songbirds. Songbirds whistle. They really only produce one tone at a time. So you can generate that tone with one direct digital synthesis synthesizer. And then if you modulate that frequency that that synthesizer is generating correctly, what's correctly mean? It means you look at the spectrogram of an actual bird song you map the frequency sweeps to functions, mathematical functions, and then you implement those functions so that your own direct digital synthesizer is doing those frequency sweeps at the correct timing. And for songbirds that are singing basically just one tone, you can generate exquisite simulations of these things. And then what's fun is you can morph them. So you can make a weird version of the songbird, and then you can take them outside and mess with the real birds. And it actually works. You can actually go do that. All sorts of robots, right? Any robot that you wanted to implement, you could implement. We've seen little crawl around on the floor type robots, and then we've also seen robotic systems, things like plotters, right? So drawing motors to move in 2D a marker on a piece of paper. There was one group that set up a pulley system with a whiteboard marker in the middle. So it was this weird set of coordinates, and they figured out how to draw by pulling the marker in these oblique angles. You could do speech vocoders. So this is kind of interesting. So suppose you talk into the microphone, and you want to figure out the frequency content of your voice. One method by which you could do that is compute an FFT, and that tells you all the frequency content of your voice. Alternatively, what you could do is set up a bank of filters that sort of overlap, so that there's a bandpass filter for this range of frequencies, an adjacent bandpass filter for this range of frequencies, and so on and so on. And each of those filters would output, the approximate amount of power at that range of frequencies. And then you take the power in that range of frequencies and you use it to set the amplitude of a direct digital synthesizer at the center of that band and play it back. And what you can end up with is a sort of weird synthesized version of a human voice. And the less synthesizers that you have, the more sort of strange and sing-songy it becomes. Does anyone have an intuition for how few frequencies do you require in order for the voice to still be understandable? But it's less than you think. I think it's like 8, right, Bruce?
So if you use predefined frequency bins, it's 8. If you use the spectrum itself to determine the best frequency using an autoregressive technique, it's 3.
Jeez. There's something interesting in there about information content in voice or something. You could do, how much time do we have? Oh, we're over time. Okay, so let me just briefly mention these others and I won't talk about them. Sonify a data set. Take a DNA strand, associate each sequence in that DNA strand to a sound, and play the DNA sequence. Sonify other data sets. You could sonify the temperature history of Ithaca. That'd be kind of interesting. Okay, that's all I got. We can talk more about this in lab.